card here to sort. I need to make a lot of people co-host today, right?
Are we finishing Reza's first?
Yeah, I think we could do that. Yeah.
Yeah, I think so. Yeah.
Okay.
So I'm going to share my screen. All right. This was based on some notes that we did on being an event. So I guess we covered the
I think you opened the Karatani one.
Is it?
It looks nice. You're
Yeah,
developing your PowerPoint skills every day.
Share a screen. Okay, so let's attempt that one again. How about this one?
There it is.
Yep.
All right. So I guess let's just start with this. We covered up to the proof that being an event provided for the existence of generic, but that proof was something that an ontologist has access to, not an inhabitant of the word S. So I guess the rest of this is there are few steps that must happen. The first step is accessing to the existence. The concept of generic is something that the inhabitant has access to, but the actual construction of, the actual existence of the generic, as well as the way to extend the ground model so that the generic exists in a hypothetical new ground model is done through not directly manipulating the elements of S or elements of the ground model, but through a method what Badiou refers to as naming. So, these slides refer to those parts. So the first thing is you have to define what naming is. So name is a multiple. So let's just read it. At this point, we know G exists for the ontologist who is not bound by the condition of absolute, the way the inhabitant is. On the other hand, for the inhabitant of S, G is definable but non-existent. The way forward is to provide from within S a way for the inhabitant to name the generic filter. This requires a schema for naming that can be potentially used to name the elements of G. In order to proceed to naming, the first step here is to define what a name is. So name, there are 6 things that we define name. Name is a multiple. Each name belongs to a nominal rank. There are multiple names in each rank. Each nominal rank is designated by an ordinal. The name multiple consists, the named multiple, or the name multiple, I should say, consists of pairs, a name of the lower rank, and a condition, and the empty set is the name of the 0 rank. combining the above, we have this formula that if a name designated by letter mu is of the form at the 0 rank is of the form of a couple or a tuple of empty set and a condition, where the condition belongs to the set C, the set of all conditions within S. And if it is not in rank 0, it is a name is a set of tuples that contains another name where pi is also the same, is a condition. In the above, mu is a name at an arbitrary rank alpha, and mu prime a name at an arbitrary rank beta, alpha and beta being ordinals, where beta is less than alpha, and pi is an arbitrary condition. Given this definition, the name at each rank is defined using the name of a lower rank. This gives us a hierarchy of names in which a name at a higher rank contains its definition. In its definition, names at an immediate lower rank. The definition of names is a nested definition similar to pure sets, such as von Neumann set ordinals. Each set contains as its elements other sets that have already been defined. This nested relation continues till we reach the bottom. At the bottom, we then have only sets, the empty set names follow the same structure, with the difference that names comprise of pairs of name that is already defined and a condition that belongs to C. So the first question I had actually was, is the cardinality of a name greater than 1? And if so, in the definition that we had, that a name at rank n is comprised of a set of a name, all the names, or a name, or names, I should say, at a lower rank, and pi that belongs to C. If we say that, Badiou does not say this very explicitly, but here and there you can obviously say that what he says is that names are multiples of this form, multiples that contain elements of this form, I should say. If each name has more than one of these elements, then pi must be a free variable, because pi at n-1 is a fixed entity, and if pi equal to C is also a fixed entity, then you have only one tuple in pi, which makes the size of pi equal to 1. Now, assuming that pi is greater than 1, which is, I think, is the correct assumption, we will have a matrix of ranks and names according to this construction. So this is the matrix starting from R0. This is a name at rank 0. This is the first name, and we have many, many names at each rank. All of these names have are of this form of empty and pi, but they have various different conditions. So you could have many, many names at this rank. Also, R1 have many, many names, but all the names in all of these N1I or N1M are names that whose the first element of the tuple are names that are defined here. So in N11, for example, you can have tuples of N01 and condition, or it can have many, many other names in that name. But all those names are coming from this rank. All the names in R2 come from this rank, and so on and so forth. So in general, we have, for example, the name at rank N, the name M at rank N is of this form, or is a tuple of this form, that it has a name at rank N-1 and it's an arbitrary name I1. So if it is M, there is a rank here, and there are many, many, many names here, and this could be one of those names here, one of those names here, so on and so forth. Badiou refers to the above matrix as the name hierarchy. Let's call it R. He adds that this matrix is not a set since it consists like L. So the first question is that is the name hierarchy intelligible to an invariant, to an inhabitant or the inhabitant?
Could I ask a question here? So
Sure.
the name hierarchy, it's basically like, I guess like a sequence or like a set of cumulative
Yeah, it's a
set
class,
hierarchies,
exactly.
but on
So
different levels, right?
right. So each of these ranks include many, many names. The names in this rank are not repeated here, but are used here.
Yeah, so then every row is like a universe of sets.
Exactly. Oh no, each row, I think, he doesn't say that, but I think each row is a set, but the whole thing is a universe.
Okay.
So let's recap what absolute is. So in order for something to be visible to an inhabitant, it has to be absolute. Let's recap what absolute is. A formula lambda is absolute if its correctness in set A is the same as its correctness for the theory, for the entire set theory. Or in another word, lambda x in the correctness of lambda x in A, in set A, implies the correctness of lambda for entire set theory and vice versa. The example of this is ordinals. When we say alpha belongs to A and alpha is less than B, this is correct both in A and in set theory.
Okay, so it's saying, wait, can you go back again?
Sure.
So it's saying absoluteness is when it be this, some property lambda being true locally is the same as saying that it's true globally, right?
Yeah, and the
Yeah,
other way
okay.
around.
Yeah. So this is, I think, what we'll get to later. This is what Badiou at the end of Logics of Worlds means by like a body treating points. Is exactly when the points, which are these local things that can be locally stated, that get a global.
Just one question, just so to make sure the connection is clear to me. The name is a multiple, but that multiple is a subset of the power set of the situation anyway, right? In Badiou's terms.
This is a name, which is clearly a set.
Sure, but that name,
right.
I mean, the name is actually part of. It's a subset you could extract with a formula from the situation.
Correct. Is constructed according to a formula. So the form, you can say that you have a formula sigma, and this formula builds a name according to this schema.
Yeah, because I mean from my vague understanding, let's say what will make this impredicative from the standpoint, from a constructible standpoint, is that it's not that the names, the subsets of the situation, these multiples are unnameable. It's the ordering structure of these names, of this hierarchy of names, that will make them increasingly hard to locate from the as a subset in the power set of constructible parts, right?
Okay, I didn't quite understand your question, but the way that I understand it is that we are familiar with set S. Everything that is within set S is accessible to us. What we are saying is that within set S, we are going to just construct through a formula that is absolute, or we claim that it's absolute, or we show that it's absolute, other multiples. We call those multiples names, right? Now, those names that we are constructing will not be in S, because there are many more of names that there are in S, but we are capable of building a formula within S that is absolute, i.e. we know, we can verify that this formula is constructible.
Yeah, my question, I think I can rephrase it. It's just that we know that Badiou, he wants to talk. The interesting thing about like Cohen and so on for him is that departing from the sort of interpretation of ZFC where sets are, let's say, things are, let's say, the basic structure of how things are presented. Minimally, they are counted. And power sets are how is the space of possible representations, right? You can, for every subset, you can extract from that set, it belongs to the power set, right?
Correct.
So when you say, you're talking about names, actually we had a theory of names, a more, let's say a weaker theory of names from the way that sets relate to power sets in being an event, right? The way he interprets this relation. So my question is at the level of these names, in the hierarchy of names, is it at that level that we already introduced something which is unintelligible from the standpoint of the original world, right? The original situation? Or is it the way they are ranked and that they're being composed together that starts to introduce a multiple that is not already counted in the power set, right? Or meaning that the names would be. Because I know that he wants to get away from the idea that when something new is produced, it is absolutely new in the sense that it's unnameable. Well, its parts are well known. If you're a regular conservative inhabitant of a situation, you're never confronted with the new in the sense of, oh my God, I have no words to describe this. You always have old words to, let's say, project it back. You will lose something, but you can always say, oh, these people are not meeting to do something interesting. They're just, kids playing. There's always an old name, right? So my question is, are these multiples that he's calling names and that are organized in these nominal ranks, are the names themselves, the multiples themselves already included in the state of the situation, right?
I think names are neither in the ground model or they are in the power set. Names are multiples that are completely a new situation altogether. Or at least this schema. Later on, he filters this schema to what he calls a nominal rank. And when he filters that nominal rank, he filters this schema to only include those names that have a connection to the hypothetical set, which is G. And then he extends the ground model with those nominal ranks. And then he says, in that extension that contains names of S and bunch of other names that we added to the names of S by nominal ranking, then we would have a new generic, we have a new model, which is SG, that is a superset of S, so that everything that is in S belongs to SG, G belongs to SG, and there is no ordinal that S has that the SG doesn't have, and there is no ordinal that SG has that S doesn't have. So thereby the structure is the same. So basically SG is a new set which basically includes G because it has all the names that belong to G. But this schema itself has nothing to do with S in terms of elements or a structure. This is just a schema to show that we have a formula. We can use a formula that is completely absolute in order to build resources that we call names. Is that clear?
It's clearer, let's put it like that.
Okay. So let's continue. No, I mean what I said. I don't know whether what I'm saying is exactly what Badiou meant or Cohen meant, but this is my understanding. So the first thing is to say, okay, this is the schema that basically creates this universe. This schema is absolute. So we understood what absolute is. We need to show. Sorry, I'm going to the wrong page. We need to show that the formula has this property. Being absolute is important, obviously, because inhabitant only has access to absolutes. If the cardinality of S is omega 0, which is one of our assumptions for choosing a ground model, and if lambda is the first limit ordinal greater than omega 0, then we know the size of this hierarchy is less than, sorry, not omega delta. So that's the first thing, because in order for this to be absolute, the cardinality has to remain less than or equal to omega 0. So let's re-examine the question again. Is the concept of name absolute? That is, the names that we define general ontology are concepts that the inhabitant can use to name the multiple of S. The answer is yes, the answer that Badiou provides. Actually, I did not see that he goes through a formal proof for this, that this scheme of naming is the same for lambda x, the same schema naming exists. So if that schema of naming is valid inside this, it is valid in for set theory and vice versa. I guess we have to take his word for it. That if this schema is lambda, we know that this is correct. But I think it's kind of intuitively correct, because in this schema that we are building this universe, we are not using any operation or any element that is outside of lambda. And if the ontologist can build this, every name within this sequence is something that is comprehensible or constructible by the inhabitant. But there is no formal proof for that.
Can you remind me the connection here between the forced statement lambda and the generic subset which is added, right? That's like,
oh, we haven't added yet.
okay.
We're adding it here, 2.8. The next step after defining a name in an absolute way and such that both the inhabitant and ontologist comprehend and agree upon is to give the names we build a referential value. Now, we built a universe, which is this, Now, one way, a simplistic way to understand the extension is now we are trimming down this universe, trimming down only to those names whose condition belong to G, whatever G may be, right? So that is, that's what nomination means, or nominal rank. Is to give names we build a referential value tied to the indiscernible G. This step requires to work backward. That is, we now work from the supposition of G. We just assume G is there. The goal of this step is to provide a procedure, another formula, according to which the inhabitant can assign to the name. So every step that we are doing in here are a constructive, according to the constructivist Bible. We keep coming up with different formulas. The goal of this step is to provide a procedure according to which the inhabitant can assign to the names created in the previous step or rank a value depending on whether a name has at least one element in its rank whose condition belongs to G. We define the concept of referential value. That's the first thing. For a name by saying if name mu contains an element mu1 pi, and if pi belongs to G, then the referential value mu1 belongs to the referential value of mu. So this is, we designate the referential value mu as Rg of mu according to the above definition. According to the above definition, we can write this, that the referential value of name mu1 belongs to the referential value of name mu if and only if mu1 and pi belong to mu and pi belongs to G. Like before, this is a recursive definition. So similar to before, we will unwrap this sequence to rank 0 where names contain elements of the form empty set and pi. We then say this: Rg of mu, the referential value of mu at rank 0, is equal to 1 if and only if there exists a tuple in the name mu at rank 0 whose element belongs to G. That is, if only one element of mu is connected to G, its pi or its pi belong to G, then the rank we assign to the entire name is 1. Otherwise, the rank is 0. And in general, the definition of the referential value of a name will be as follows. The referential value of mu are referential values of mu primes if there exists a pi within mu prime, within these tuples, where the tuples that belongs to mu, whose pi belongs to G.
Wait, so this should be saying that Rg sub mu is equal to the set of Rg mu primes, right? Where there's a pi, which is an element of the condition for the mu prime and is in the original mu, and pi is in G. Yeah, this is the gluing together. I don't know if you saw, I can go back to this later if I get to it, but how you can reinterpret the names as constructing sheaves over a poset, but you do, I don't want to get too into it, but this is the step of when you take the sheafification of all of them and then you glue them together by an equivalence relation. That's what it is here, is when they agree on an element of the generic set, which can be an ultrafilter or whatever.
So if we come back to this, if we take this this name that belongs to rank n, and it is the mth name in rank n, which has these names. So the referential value of these names would be, you look at each element within this, right? And you say, okay, so this referential value, this name, right? You have this name. If the condition in this name, in this tuple, this pi at n minus 1 j1, if this condition belongs to C, then the entire tuple, or the referential value for this name, I should say, belongs to this. Otherwise, it doesn't belong. So this is a way to trim down these names from those tuples whose condition do not belong to G. So if this is a universe, you're pruning this universe from a lot of elements according to this schema. In the above definition, the goal is to designate the name mu of the rank alpha with a referential value with respect to G. The name mu has elements of the form mu prime pi, where mu prime is a name of the rank beta, which is lower than alpha. For each pair of such name, if its condition belongs to G, then the whole pair resolves the referential value of the name element of the pair. This way, the name mu is expanded to a set of referential values of the names of the lower rank. This is a quotation from the book. We will then constitute in a single step another situation than the fundamental situation by taking all the values of all the names which belong to S. This new situation is constituted on the basis of the names. It is a generic extension of S. Announced earlier, it will be written as S extended by generic. So coming back to your question, Gabriel, this is not an extension. This is just a schema to create names.
Yeah.
Create resources. This is the extension.
Yeah,
So
if we
Yeah, that's what
take a step back, I think what's happening is we're basically faking Gödel's constructible universe by taking some initial sets and then using transfinite recursion, we're building the cumulative hierarchy of definable. So like with the assumption that the universe is constructible, we're taking all definable parts of the lower rank and adding them to the next rank, right? But
Exactly.
the power set. So because it's a power set means all possible combinations of definable parts in the previous rank exist in the next rank, and so on. And once you build up this hierarchy, you have basically the constructible universe. And then the mysterious part to me is like you have this G already. Maybe previously we've defined G, but that allows you to select the connection between the sets. So the relation of belonging is kind of tuned according to what follows from G, right? I mean, that's the big step here.
That's the biggest step. That's the biggest step. And if you are the ontologist, I guess, the only thing that you're telling the inhabitant, the formula is comprehensible. The only incomprehensible part of this formula is that you don't know what conditions belong to G, right? But if you say, let's assume G exists, right? The existence of which is not proven to the inhabitant, But if you make that assumption that G exists and it contains a bunch of conditions that belong to S, to the ground model, then with that assumption, this formula is comprehensible. And I like this comment. I should add to this, that each of these ranks is kind of a transitive inclusion of the previous rank. So it is constructible in that way. Gabriel, you wanted to say something?
No. The way that you guys described it now seems closer to what I was thinking. That it seems to me that, again, speculatively, what's going on is that we need to organize a certain hierarchy of infinite subsets so that we can then attach them to a reference in G, right? So the names themselves, these infinite subsets, they don't contain anything that is not accessible in the, let's say, pre-evental situation.
Yeah, and
So,
and it's
okay, go ahead.
one more thing is the relation between C and G here. So like C seems to function very similar to the, at least on some sense, like the transcendental, because you're able to basically modulo out certain conditions. So this pi element, which is the second part of the tuple, that must belong to G. If it does, then this RG function, which this RG function is very much like a point in logics of worlds lingo, because it given any name, it tells you either 1 or 0, right?
Yeah.
1 if the condition belongs to the generic, and 0 if that condition doesn't belong to the generic.
Absolutely.
So then in that sense, the conditions function kind of like a transcendental, except there is no minimum. It's I think, potentially atomless partial order. So it's not exactly like a transcendental, right?
Yeah, so I think you do actually get the transcendental here, which is just the underlying poset, which I think from the names definition is not completely obvious, but for every one of these cumulative hierarchies, you always start with basically like an empty set and you build off from there recursively, but you can build off recursively like at each stage multiple times, right? Like however many names, like, I mean, that like split, like if you imagine like the minimum node, which is like the empty set, and there could be multiple of them for different ranks, I guess. But if the first element's not the empty set, then the first element is a previous name. So then on the next level, their first element is going to be like the set containing the empty set, and it could be a number of them, right? So then it defines a poset all the way up. And isn't it G is then a generic filter on that poset, right?
Isn't the M, so in that little table here, it's like there's 0, 1, and then 0 to M, right? Isn't M on the first rank 0?
This should be N.
No, not this one, but the row, the end of the row, the first row. You see there's an M there. Shouldn't that be the length of C? Or the cardinality of C? Because by the definition of name, where you say on the left side of this slide, name is either, and you have these two options, right? The first one, when you're on rank 0, pi belongs to C, meaning at most you can have C number of tuples. Yeah. So in rank, is it true in rank 0 that you can have only?
At most, yes.
At most not C elements.
Yeah, at most. So
what's
the
C
length
again here?
C is the set of all conditions within S.
Okay.
Right. So if C contains if the cardinality of C, whatever that cardinality is, the length of this row, the length of this cannot be greater than the cardinality of C. But in practice could be a lot less, at least for condition 0, right?
Yeah, then after that it blows up.
After that, it blows up because it can have names from different places, and it's like a Cartesian product of names here and the cardinality of C. The maximum is the Cartesian.
So then you have however many rank 0 names you have is like your number of empty sets, kind of. Right?
Yeah, so here, the maximum number that rank 0 can have, according to the schema, the maximum number of names is the cardinality of C. But within rank 1, now you can mix any of these names with any condition in C. So maximum would be the cardinality of C multiplied by cardinality of C. So this rank is that. Then this rank is way bigger than this, and this, so on and so forth. That's why this is not a set, this is a universe, probably. Okay, so there are two things that we want to prove after this. We want to prove that S is a subset of this extension. And like I said, this extension has the same structure, i.e. by structure, Badiou says that SG does not have any ordinal that does not exist in S. So basically, SG does not add an ordinal. So the first one, I guess, goes first. In order to show that S is a subset of SG, we want to show for all alpha belonging to S, we have alpha belonging to SG, but SG is a multiple of names. This means that we must show that for any alpha, for all alpha belonging to S, there exists a mu that belongs to SG, such that mu is the name for multiple alpha actually in S, or the value of the referent in the extension is alpha. But the name SGs are not fixed. The names in SG are not fixed since G is not fixed. So since we don't know what the names mu are, because names mu depends on G, and G is not fixed. In light of this issue, our general strategy must be able to show this. For the quotation, for every element alpha of S, there exists a name such that its referential value is alpha, whatever the generic part. So for this, we can rely on the belonging of empty set to G, which is absolute whatsoever, whatever G is. So all the names of the pairs of the form mu and empty set. Now, notice that how empty set changed position. Now empty set is the condition, right? So in this, we all of the sudden that we have conditions. A lot of these conditions are not empty sets, right? We take out of this only those combinations of names with empty set, where these pies are empty set. For this, we can rely on the belonging of empty set to G, which is absolute. whatever G might be. So all the names of the pairs of the form mu and empty set should belong to RG mu, whatever G might be. For an arbitrary element alpha belonging to S, the canonical name is defined as follows. So Badiou now defines what is called canonical name. So canonical name at rank alpha is the names of canonical name at rank beta where all the conditions are empty set. This form of the name for an arbitrary, so again, this is another filtering, this is another funneling of these names of this form. Now from the names of this form, we are just taking those names that have a condition of empty set, and we call those names the canonical form. So this form of the name for an arbitrary element alpha of S is correct and absolute. It is correct due to the definition of the name, and it is absolute because it relies on the names of the previous level that have already been defined and an absolute condition, which is empty set. So there is no debate about that because we assume that C includes empty set. Now, this is the crux of the affair. The referential value of the canonical form, canonical name mu alpha, is alpha itself, whatever the supposed generic part. We always have R of G mu alpha is equal to alpha. These canonical names invariably name the multiples of S to which we have constructively associated them. So that's the point. So the point is that alpha, the canonical name for alpha is the element alpha itself. We know that from before, from the previous section, that Rg of mu alpha is equal to Rg of mu beta, where beta belongs to alpha. We can say that because the canonical name mu alpha is a set of pairs of this form, and we know mu equal to belongs to G. This means that this referential value will be the set of the referential values of this form. But since mu beta is itself a canonical name for beta, then the referential value of the latter canonical name is beta itself. This simply means that the referential value for alpha is a set of all betas that belong to alpha, but this is alpha itself, because alpha is the count as one of everything that belongs to alpha. But what this means is that for every alpha in S, we are able to find a name in SG. And this shows us that what we have set out to prove, which is S belonging to SG. So basically, to prove that, we say there is a tiny portion of SG that we defined a way to extend S to SG. We defined a schema to build names. And then from those names, we only chose a tiny portion of the names within the universe of names whose condition belongs to G. And we created a new situation through this formula. Then we said, we want to prove that all the elements in S have a name in SG. In order to show that, again, we funneled a tiny portion of SG, only those referential names or referential values whose condition is empty set. And we showed that every element within S must find a name in SG according to that canonical form. So SG is way bigger than S. because it only are picking out names from SG, from those conditions, from those referential values whose condition is the empty set. In essence, what this proof shows is that SG contains names such as that for any element alpha of S, we can assign a name from this extension such that the belonging structure of S remains intact. The structural part, the other condition, is guaranteed because for all the nominal pairs of this form, mu, beta, and empty set. So everything that belongs to S now has a nominal ranking or a referential value of this form. Belonging to the canonical name of alpha, by definition, we ensure that beta belongs to alpha. This shows that inhabitant can conceptually accept the fact that the situation in which she lives is part of a universe that is acquired by nominal expansion of S using the nominal projection based on G. This is absolute because we only use the condition empty set. But SG is still a concept, granted that we have established that S is a subset of SG, but we have not shown to the inhabitant that G is in SG. G is still too hypothetical and not enough existential. Now we need to show that the extension of SG does not add a new ordinal to S. The preceding result tells us that all ordinals in S belongs to SG. Therefore, with this proof, we would like to show that S and SG have the same ordinals. This is an important result because it shows that the generic filter is incompatible with an ordinal. This point indicates the proximity of SG to S. It signifies that the natural part of the generic extension remains that of the fundamental situation. Extension by the indiscernible leaves the natural multiples invariant. The indiscernible is specifically the ontological schema of an artificial operator, and the artifice is here the intra-ontological trace of the foreclosed event. If the ordinals make up the most natural part of what there is in beings as determined by ontology, then the generic multiples from what is least natural, what is the most distance from the stability of being. But how can we prove that extension of S by G does not add to new ordinal to S? Let's suppose the opposite. Let's suppose that there is an alpha in SG that does not belong to S. Furthermore, let's suppose that alpha is the smallest of such ordinals. That means that if there is any ordinal less than alpha, that ordinal belongs to S. This means that both alpha and beta will have canonical names in SG. In particular, canonical names, mu alpha will be shown as this, which we have seen before. It's obvious that according to that, the canonical name for alpha would be the nominal ranking of alpha. Mu beta is also a nominal rank whose referential value is beta. What is the nominal rank for canonical name mu beta? Its nominal rank must be at least beta. It could be also greater. How can we show that? We show that by recursion. The nominal rank of mu of empty set, the nominal rank of an empty set, or the name of the empty set, or the nominal rank of the name of empty set is empty set by definition. Let's suppose this property is also holding for ordinal gamma. That is, the nominal rank for gamma, mu of gamma, is equal or greater than gamma. We want to show if gamma belongs to delta, then the same property holds for delta. This is That is, we want to show that the nominal ranking of the canonical name mu delta is equal to those tuples of that contains names with the multiple gamma and the condition empty set where gamma belongs to delta is equal to greater than delta. But we know the latter canonical name mu delta implies in its construction canonical names of the form mu gamma. And therefore, according to the definition of the names, its nominal ranking should be greater than the nominal ranking of those names of the form mu gamma, which according to the above assumption is equal or greater than gamma. But what is equal to greater than gamma is delta. Hence, the nominal ranking of the canonical name mu delta is delta. This completes our recursion. According to the above recursion, we can then conclude that the nominal ranking for the canonical name mu alpha is equal to mu beta with the condition empty set where beta belongs to alpha is consequently at least alpha. But that leads to a contradiction. Why? Because we assume that alpha doesn't belong to S. But we just proved the rank of the canonical mu alpha is alpha. But how can a canonical name in S has a rank that is not in S? The answer is it cannot. We agree from the get-go that everything that has to do with the nomination must only use the resources in S. Even elements such as G that is not in S will use only resources in S for nomination. I think this is very important and very interesting, because this is exactly the crux of where Cohen's, like I guess Dennis said or somebody else, that is, we are using exactly the method that constructivists use, or Cohen used that method in order to basically show that we can construct something that does not belong to the set. Is Yasha saying that he has to leave?
His computer battery died out. He's coming back in a minute.
Okay. But clearly the canonical name for alpha requires an ordinal ranking alpha that is not in S, which is a contradiction. From this, we conclude that there cannot be any new ordinal in SG. SG will have the same ordinals that belong to S. In the end, the extension is neither more complex nor less complex than the situation. Piece of cake, right?
I got lost at some point in this slide, but I think I get the gist of it. It sounds like this nominal rank functions like a kind of synthetic belonging, right? We're trying to construct belonging from the ground up using the names. So a name is always the name of a condition, right? And a condition is something that maps elements of some set to 0 or 1, let's say, or something in between maybe. But conditions basically tell us like this should be in the generic, right?
Mm-hmm.
And if I have two conditions that conflict, like I can't choose both, right? One condition says, well, 1, 2, 3, and 4 need to be in the generic. The other condition says, no,
Yeah.
one should not be in the generic, but 2,
G
3,
is a
and 4.
filter. Yes, G is a filter. So
Exactly.
So it cannot have contradicting conditions.
Exactly. So there's this consistency condition. So if you so names have to, when you choose the name of one thing, you exclude the names of a bunch of other things. And actually, I think it's possible that two names can refer to the same condition, right? I think you showed that in the previous. when you talked about the reference.
Yeah, they can combine with any condition here, right? So that's why I named this name. I didn't name them from 1, 2, 3, right? Because names at this level, this name can pick out any name from any part of this previous rank. So they all belong to that rank, which is n-1, but could be I here, or I1 here, or I2 here, so on and so forth. Not each name in this rank includes all the names here.
Yeah,
Or at least there is no
selection. Yeah,
some selection. So there is a choice function here, right? That you can choose names from anywhere here. So if it is this name and another name on this rank, like N1, this name and this name, they don't select the same names. They could select different names. Sorry, go ahead.
Yeah, and then so once you have these conditions and you have this consistency, basically like trying to construct this filter. This filter is constructed by pasting these conditions together, like Joshua was saying, along the generic, right? You're pasting them together such that they don't contradict each other. And it's possible that two names are compatible with each other. So then they can be pasted. They can basically be considered compatible. And then once you have these names, then you have this, the next move here on the slide on the left, which is the name can be used as a function where you pass in an ordinal. If you give it the ordinal, it gives us the set of the condition of mapping another ordinal. Okay. So the empty set means that there's belonging there. Okay. The way I'm thinking of it, I could be totally wrong, but the way I'm viewing it is very much like the transcendental, where there are kind of like degrees of belonging. And in the case of, in this notation, when your condition is the empty set or the topmost condition, that simply says that beta belongs to alpha.
Yeah. So in summary, like I said earlier, I think the way that I understand it is that you create, let me see if I can write somewhere here. You create a universe of all names. This universe of all names basically takes empty set, starts from takes empty set and a condition from C, right? Now at this level, C is not a filter. So at this level could be contradicting filters, okay?
Mm-hmm. Yeah.
And then at each level, we saw that at each level, so at each level, then you reuse these names that you built here, and you go to additional ranks. So the general form would be name and condition. Can't type. So this is the general form. Each name and condition at each rank, the name part comes from the previous one. So that's a step one. So this is a step one. So you build bunch of stuff. At this point, I just call them resources. They are names. Okay. Step number 2, you connect these names to G. Now G is a filter. So you go through all these names and you take out all the names in each rank. You take out the names that don't belong to G. So you remain with a bunch of names at each rank and some condition where condition belongs to G. So this is now, a lot of these names are pruned out according to this schema. Okay. Now you extend, now you say that S is a set, and I add the elements of these elements that I came up with to S, and I call it SG. But what is SG? SG is just a set of names. So the claim is SG is a set of names. So the claim is that the set of so let's remind ourselves how we built SG. SG is this actually. SG is a set of names. Is not the set S with bunch of names added to them. Extension of S is a set of names, right? Set of names built in this way. So what we want to show here is that the set of names that we built in this step, like this, through this definition, this set is S belongs to this set. But how does S belongs to this set? S are elements, whereas this is name. So we want to define another concept, which is called canonical name. And we want to say that each element, and that's what the quotation I brought from Badiou that says that this is the crux of the matter, that each element is S, is named by its canonical name. And all the canonical names belongs to this set. Therefore, S belongs to this set. That's the way you understand the proof extends. And then later on, we want to show that this set of names does not contain names of new ordinals.
Do you have an understanding of what, if it's not containing names of new ordinals, what is it adding that S didn't have before, right?
It's the name of the conditions in G. And that's the next section. Relation of G to SG. Similarly, it is important for us to know what relation G has to SG. In particular, does G belong to SG? If so, does G remain indiscernible in SG? We will now prove that G belongs to SG. Now remember, G is a subset of S, is an indiscernible subset. With SG, now all of a sudden, we are adding a subset of S as an element of SG. That may appear as an odd question at the beginning, since SG was constructed using a nominal projection based on G. But we must remember that the construction of SG was through the operations that was accessible to the ontologist and not the inhabitant. This step proves that G is available to the inhabitant. That is, G belongs to SG. But as we mentioned above, we still have not shown to the inhabitant of S that G belongs to SG. Moving on. To know whether G belongs to SG or not, one has to demonstrate that G has a name in S. Again, there are no other resources to be had apart from those found in tinkering with the names. Kuhnen puts it quite nicely as cooking the names. Consider the condition pi that belongs to C, which by transitivity of S, we will have pi belongs to S, which by the result we just proved the canonical name for that condition belongs to SG. Now consider the following set. The name of G are the name, those tuples that has the name of pi and the condition pi, where pi belongs to C. The above definition is for the set of all ordered pairs constituted by a canonical name of a condition, followed by the condition. This set is a name by the definition of names, and it is name, it's a name in S. What does it take for mu of G to be a canonical name? It would be a canonical name if pi belongs to G. But if that were to be the case, then what is the reference of RG mu of G? This would be the reference of the canonical names of pi's when those pi's belong to G, which is G itself. Hence, we have RG of pi G equal to G. What is the real semantic of this? We have been able to fix a name for G, but not the G itself. The name is discernible relative to what G might be, but G itself still remains indiscernible in SG. So whatever G may be, it always has a name in SG, which proves G belongs to SG. This is an amazing result for the inhabitant because without her discerning the generic filter, she knows that the generic filter belongs to the generic extension. This is precisely the result we were asking for. Having established the fact that G belongs to SG, the question we are now asking is whether G is indiscernible for the inhabitant of SG. Badiou says this question is crucial because we are looking for a concept of intrinsic indiscernibility, that is, multiple which is effectively presented in a situation but radically subtracted from the language of that situation. The response is positive. The multiple G is indiscernible for an inhabitant of now this universe. No explicit formula of the language separates it. Oops. Let's suppose G is discernible in SG. By the definition of discernibility, this means that there is a formula such as this in SG that separates G. We know in this formula the condition pi belongs to C. But what about parameters alpha 1 to alpha n? If all of them belong to S, then lambda had existed in S, which would have made G discernible in S. This means all or some of these parameters must not belong to S. That is, they only belong to SG and are supplementary elements as the result of the extension of S by G. Let's say at least one element parameter alpha 1 is as such. If that were to be the case, then the name mu of alpha I is a regular and not a canonical name, because if it was a canonical name, obviously it belonged to S. Which means its definition, it requires the precise condition pi I that is in the constitution of this name. This means even prior to being able to separate G, we need to know which of its conditions is in the definition of one of the parameters that is in the formula that defines G. This is a contradiction, which means G is not discernible in SG. Thus, for an inhabitant of SG, there does not exist any intelligible formula in her universe which can be used to discern G, although this multiple exists in SG. It is indiscernible therein. We have obtained an in situation or existent indiscernible. In SG, there is at least one multiple which has being but no name. So G is both indiscernible in G and SG, but this indiscernibility has a different semantic, meta-ontological meaning. In each case, we must be recognized therein when it exists in the first situation under the supernumerary sign G is nothing less than the purely formal mark of the event whose being is without being, and when its existence is indiscerned in the second situation, nothing less than the blind recognition by ontology of a possible being of truth.
Can I ask can you clarify a bit about G being indiscernible in the extension as well, right? Because it was my understanding that it's indiscernible from the previous standpoint, right? It's indiscernible in S.
Yes, so it is indiscernible in S. Well, it is indiscernible and inexistent in S. Right?
Yeah.
We are building a subset of, so first of all, G is not in S. It inexists in S. It's not indiscernible, it just inexists. The property that G has is that there is no formula that you can assign in order to name G, name what G is as a subset.
From the standpoint of S, right?
From standpoint of S.
Mm-hmm.
With SG, now you're building a new situation of names that includes G, because G itself has a canonical form, canonical name, and that canonical name exists within SG. So we know that since the canonical name for G exists in SG, then G itself must exist in G. But in order for us to separate G from SG, then we have to use formula like this in order to separate SG. But in order to use a formula like this, you already have to know what G is. So it's a circular condition.
Mm.
I think that a good way of understanding what's at stake is that, I mean, let's put it like this. If the whole generic thing was meant simply to state there is something we cannot fully name in S, but you can mess around with things in such a way that it is fully named in the extension. Truth for Badiou would be like a vanishing mediator between a situation where we know a lot of stuff and a new situation where we know a bit more, right? And I think that that's not what he wants with, that's not what he found in the way that he reads this, is rather that the type of situation he wants to make more thinkable, to give us more resources to think. For example, it's highly subjective things like being in love, where you wouldn't say something like, before I fell in love, I didn't think this was possible, but once I fell in love, I can actually explain what's going on. I can just refer to it, point to it. It still remains something that has a tense relationship with knowledge, but there is a new kind of knowledge that is part of a, for example, loving relationship that allows you to navigate this thing that you still cannot pinpoint, right? Otherwise, it would be a process like some status quo, the emergence of a new subset, and then a new status quo that has just reabsorbs it, and you have, you know, like a change in paradigms or something like that. It's just a knowledge paradigm, then a new knowledge paradigm, and ultimately they are all kind of the same, right? Just with more stuff. I think that the idea that something remains indiscernible in the extended situation, but
Well,
now
I think
you
the other, sorry, go ahead.
right, but there's a difference between something indiscernible being the situation, and you can only see the old, like you can only speak as if there are only old stuff, and something indiscernible being there, but you can speak about its novelty. That doesn't mean you can exhaust its novelty in terms of knowledge, right? So truth gains a bit of being. That's why I think it's so important for him. Like otherwise, truth would be like a passage point between two knowledge structures, or whatever you want to call it, right?
Yeah, I
I
like
think,
the implication that the S and SG are very close together, right? Like their difference is like minuscule.
Yeah, I think that's important, right? I mean, so yeah, Brez, I didn't want to.
Well, I just wanted to say the paradigm that I understand from this is that the generic extension is not built by knowing what generic is, right? Because we never know what generic is. That's why it makes it generic. Otherwise, the whole paradigm for genericity will be debunked, and it becomes a constructible world. Since from the standpoint of S, we don't know what G is, all we can say that we can construct a world where G is guaranteed to exist without knowing what that G is.
Yeah.
I mean, that's a different paradigm of thinking what truth is. Like, for example, the future society of communism, let's say. What's the word that we are built to include the truth of the generic. That does not have a definition. You cannot say now we are in a society that we call communism because we have now attained X. But we are saying that by extending it this way, we are guaranteeing that X exists in this world.
I think that also clarifies something. I was reading, I sent you guys on the chat here, but I'll send it on our WhatsApp group as well. I found this really marvelous text by Paul Cohen, presentation he gave, I think in 2001, on the discovery of forcing. It's quite informal the way he goes about it. He tells the story of how he had the idea. He compares his procedure to Gödel's and so on. And he's very clear, like that, generic cannot be a new determination because it's by definition defined as something which has no specific predicate, right? So it wouldn't make sense to just say, so now in the extended situation, we know what G is because we define G as generic because it has no specific predicate. It's not adding a predicate, right? Something that has a new predicate. So
absolutely. I mean, this is the definition of generic is that you cannot provide a predicate or a formula that defines it. So it is a singularity with no particularity.
Yeah, so I mean, that's the connection with the common, right? The common wouldn't be the end state. You had an inequality and then a new situation, you have X, which is equality, like, or something, right, in the world. It's just the proof that there can be a situation where you can have a better language to talk about something which is common. But if it is common, it has no specific predicate.
And I wanted to say something about the comment Yasha made about SG is minusculely in excess of S. I think it's not, because if I understand this correctly, a canonical name is a small portion of names that we have added as the referential rank. remember referential rank we defined as this, right? Now from this, sorry, not this, as this. In this definition, pi could have any value from C. But nominal rank, which means that names of elements in S are only those referential ranks that has empty set. That's huge. You're reducing this set to an element, to just one element of C, which is empty set. So this schema adds a whole lot to S. Huge. There are names, huge number of names. I don't know whether that makes sense to you guys or not.
And if you go back to that, I'm just confused about the notation because it says that S of G is comprised of all sets RGU such that U belongs to S, right? What RGU I thought only gives us a 1 or a 0. So this notation seems to suggest that, are we collecting all of the possible mu's such that this is true, or all the RG functions? Well, like, what are the elements here of S extending with the extension of G?
So extension of G are those names.
Okay, so it's all mu's such that mu is in S and RG of mu is equal to 1.
Well, RG of mu are all those names. So this notation, remember, we introduced here, or here, that we said we define a concept of referential value for a name by saying if name mu contains an element mu pi. So it has many elements like this. And if pi belongs to G, then the referential value of mu1 belongs to the referential value of mu.
So it flips the relation, right?
Yeah, it's sort of.
Yeah, because if mu contains an element, mu1, then the referential value of mu1 belongs to the.
So
oh wait, no, it doesn't.
Let's come here. This is a name. This is not a referential value, right? This is a name. We say within this name that has a random name from this row and a random condition from C, right? From this, if you want to build referential value for this name now, you build a multiple by going through each of these elements to see whether this pi belongs to G or not. If it belongs, then the referential value of this guy belongs to the referential value. So basically, the referential value of this guy would be the referential values of each of these tuples or each of these names, right? That are combined with an element of G. Does that make sense?
Can I just read a passage from Being an Event really quick, just because I think it captures the thing that, at least for me, would be nice to have very, very clear in the presentation, just to.
You want to present or?
No, I can just read it to you guys. Okay. This is from the chapter on the math theme of the indiscernible Cohen strategy. And the reason why I'm reading this is because
what page is this?
It's on page just 1 second. Oh, fuck. Why is my copy so?
Doesn't matter, just read it.
Yeah, now I lost it. Where is this? Yeah, here. It's on page 357. So in this page, Badiou says something that I think it's relevant, because the thing that I really want to make sure I get from the discussion today and from these 3 presentations is the connection between, we've been talking about this triangle of how things are composed determines what they can interact with and determines what is intelligible, right? So intelligibility, interaction, and compositionality, which is something it's clear for us in our project and in Badiou. And I think that this is relevant for us. But in this passage, he mentions this in a weird way in the context of Cohen. So he says, he's just explaining what we're gonna do, right? In the description of Cohen's method. He says, we'll thus start from a multiple supposed existent in the initial situation, the ground model. That is, from a multiple which belongs to the situation. This multiple will function in 2 different manners in the construction of the indiscernible. On the one hand, its elements will furnish the substance multiple. I'll just share the screen, just so, sorry, just so it's easier for everyone to follow.
Go ahead.
I'm just reading this passage, right? So this multiple in the ground model will function in 2 different manners. On the one hand, its elements will furnish the substance multiple of the indiscernible, because the latter will be part of the chosen multiple. On the other hand, these elements will condition the indiscernible in that they will transmit information about it. So this multiple will be both the basic material for the construction of the indiscernible, whose elements will be extracted from it, and the place of its intelligibility, because the conditions which the indiscernible must obey in order to be indiscernible will be materialized by certain structures of the chosen multiple. That a multiple can both function as a simple term of presentation, meaning this term belongs to the indiscernible, and as a vector of information about what it belongs to is the key of the problem. So you see, like, this is a presentation of this of the generic subset enforcing that connects this idea of composition, right, the basic material out of which generics composed, and intelligibility. So composition and intelligibility should become clearer, right, as 2 aspects of this. And it seems to me that this is very much where we are kind of struggling, right? From one hand, we have the generic subset. On the other hand, something about its structure is being transmitted through the nominal ranks and their referential values, right? They function as vectors of information, right?
Yeah, which are the conditions.
Yeah.
Yeah. So basically, in order to I mean, later on, we reviewed that. We go a lot more into this. We don't say G is any subset of S. G is a subset of the conditions of S, right?
Yeah.
So we, if you want, we can review how Badiou is presenting how to condition G. So G is basically a filter. It's an ordered set. And at the end of the day, G is a subset of C.
Let me stop sharing here.
So I don't know how you want to proceed right now. It's 8:25, and we just reached forcing. There is no way we can finish forcing tonight.
Yeah, it would be good to try to connect it to logics of worlds a bit, but I guess rather than presenting slide for slide, we could just move to the stuff that also Yasha was talking about. And
okay, so you want to go with Yasha? So I can give you a basic. Oh, I'm not sharing. Where's sharing?
If we want to go quickly, I can try to connect a couple things from here.
Okay, so you share.
Let me share. Let me share. Let's get my whole desktop. Okay, you can see. Let me start from here actually, just because we've been on the names.
Yeah.
And I'm gonna go through this and see if this makes sense though. Right. So this is the other perspective on names where so this is the sheaf construction of it, right? So what I was saying before is when you think of the hierarchy of the names, right? How every name is defined by a name of a previous rank, right? Then you get an ordering on them. So you have a poset, yeah?
Mhm.
So when you take a name, basically this is the TLDR version, is you take to construct the sheaf, which is going to be basically the continuous structure of the name, is you take this universal, you take first this pre-sheaf called P pre-sheaf, which is the one that's generated by a single element. So it's basically just going to be saying it's going to choose either 0 or the empty set, either a set containing the empty set or 0, depending on if this condition Q, right, is less than or equal to P. Okay,
Mhm.
that's how it acts. So, but you're doing this over all names P, which are in your the name of this P, right? Because remember this, hopefully this makes sense. This name is composed of many other names. So you take for all these names, you take this basic pre-sheaf thing, which is just saying for any value less than it, I'm gonna set that to 0. For everything else, the empty set. You glue them all together. This is this union, this is the co-limit. It's basically a disjoint union of everything. And then from there, you take the sheavification, which is where you, of this thing, where you take each one of the individual sections and you take them all together by this direct limit, such that their topology basically includes everything. It's like the most trivial topology in that situation. But then you give this equivalence relation, and I think this is what Reza was talking about the pruning here, that whenever you quotient out by this relation, whenever two names here, P comma Q, you say is going to be equivalent to P prime Q prime, right? At level Q, if Q is less than or equal to both P and P prime, such that it forces, they both force inequality at the level Q. So saying that two names are going to be the same if they agree on something below them in the generic filter, right? Reza, I don't know if this connection makes sense at
You
all.
lost me after the disjoint union. Can you repeat this sheafification function? So I understand this is exactly what we talked about. So simply just repeat this paragraph by taking sheafification.
Yeah, so by the sheafification is when you take an arbitrary so this is a pre-sheaf, which is defined by this name. We're just trying to get a sheaf construction of this name to understand how the name has like a topological structure on top of this poset, okay?
Right.
So the sheafification is the canonical way that you can take a pre-sheaf, which a pre-sheaf, remember, is just a contravariant functor, which it's just basically, in this case, it's a structure which is built on top of our topological space, right? It's on top of the world of appearing. It's sort of the, at least in Badiou, the sheafs are like the transcendental functor is the object that connects being and appearing. It's when you take for each set of something that appears, each stalk above it is all of the things that are basically indiscernible in that world, right? So here the sheafification is when you take any pre-sheaf, and there's always one canonical way to do that, and you do a similar process to what this is. So you basically end up taking a double co-limit, but under, I have to remember the exact, I can pull up if you want the exact, I don't think I included it here, the exact, oh, wait, that's the exact sheafification definition. And where, okay, it's a complicated thing. I don't want to get too bogged down into this. I don't know if it has the it's okay, we don't have to get into this right now.
No, just repeat the sentence you talked
Yeah.
about. So you said this is another way of saying what pruning is.
Yes. So what you do is you take you turn this pre-sheaf, which is naming each, which is taking each one of the names and gluing them all together.
Yeah.
And it's taking the sheafification, which doesn't really change the pre-sheaf at all, but changes the underlying topology such that it's more general. This is something I don't know if you listened to the beginning of the talk before, where a topology is always a choice of sort of resolution within your space. It's a choice of subsets that are considered to be, in this case, open, or you call them open, that filter sort of like what is discernible or what is sayable within your space. So the sheafification, rather than changing the being of the functor itself, it's changing the topology of the space, giving it like a looser definition, such that the gluing property of a sheaf is satisfied like immediately or canonically. I don't know if that makes sense. But then the important thing is that you quotient by an equivalence relation, which what that means is you take, so for any, these are going to be elements of the name. Okay, so they're also names. So you glue them together at a certain level. So you glue them together at a level Q, which is less than both P and P prime. Okay, whenever Q forces the equality of two things at that level. So what this is basically whenever they agree on an element of your generic subset, you glue them together.
Tau and tau prime are what? Tau and tau prime are.
Yeah, it's tau and tau prime.
I mean, in being an event, they are statements or formulas. So forcing is that if a condition within S forces a statement tau, then it means that it forces the statement to be true in S extension G.
Yeah, it means that tau and tau prime, right, are the same at level Q.
Okay. And what are tau and tau prime in this case?
They can be any elements. It's just saying that it's forced that when both one second. I might have to go back through this later and give you more specific things. I think this stuff I went through kind of quickly.
We can define the element relation of the sheaf. Maybe you defined it before.
Yeah, let me see.
So here, for some name sigma, the corresponding sheaf is the universal sheaf with a generator at level P for each point. Oh, so point is P and tau. So also called P tau.
Oh, this is why.
Yeah.
Yeah, this is why I copied it down wrong here before. These, it should be, the name
P
should
and
be
tau.
P tau and P prime and tau prime.
Tau, okay.
Yes,
That
so
makes
it's the
sense.
conditions. So it's the
Yeah.
conditions of the names being the same. Sorry,
Okay.
this was just me copying it down at the beginning, at the bottom wrong.
Yeah.
At the top, it's correctly done.
Yeah. So
Here,
that makes sense.
yeah. Yes. So that's I think that's the same as what you were saying before, right?
Mhm.
That tau equals tau prime, right? That's the
Mhm.
two conditions being the same is in the generic set, right?
Mhm.
Or is forced by it. I didn't go super deep into this specifically, but I just found this from I think I found this actually on Stack Exchange, and this is kind of like a quick go through of it. But I did want to show just really quick before we finish. I'll skip over this stuff. This is the more complicated things. I guess we just these last couple sections, right?
Oh, your slides are a lot more fun than mine.
Oh yeah. Some examples of sheaves that are a little bit more concrete. So one motivating example is we want to think about the exchange sheaf, which if we think about commodities as, right, as like fuzzy sets and exchangeability as something that is like more or less true rather than, and also something that fluctuates over space and time, then the exchange sheaf is basically the gluing properties that say what things are exchangeable with one another, and sort of like the extent to which this thing is like globally consistent has to do with like how exchangeable certain commodities are in the general market, right? So we say that a commodity itself can be thought of as a topological evaluation function, right? So this is the idea of the commodities appearing to one another, right? So given an appropriate space where we can assert exchangeability and giving a fixed commodity, we can ask for whether other commodities are exchangeable with it, right? So this is the transcendental. And then we say that two commodities can be more or less equivalent if they're more or less exchangeable. So I just wanted to start with just, I guess, this kind of motivating example. I don't know if Dennis has more. Do you have more to say about this specifically?
Dennis had to go.
Oh, Dennis did have to leave. But let me just run through really quick this in that case. Some of this logics of the world stuff. So the transcendental functor, right, which Badiou defines in logics of worlds, is actually also going to be a sheaf, right? So what it is it's taking for an object, for each part of the object, it gives you a stalk here, or actually it's better to think of it as this kind of right picture. For each element or part of the object, it gives you the corresponding parts of their being which are indistinguishable with respect to that world, right? So then if we think about it this way, then a section of this sheaf, which remember the section is right, the bottom is like the world of appearing, the top is like the ontology, right? So in the section would be for each one of these things, I'm choosing one thing up above. So here, this is like the canonical representation. So it's for each part of it, we're choosing an element such that it represents like a generic element of it that glues together all properly.
Yeah, that makes sense.
Uh-huh.
So
then
the canonical name is a very small portion of what can be represented.
Yeah, so the canonical names are exactly like this. It's taking for each one of these, this would be one of the names, and then this is what we build above it, right? For each name, there's a structure of the, not the canonical representative, but the, what is it called? The representable or whatever part. And then the canonical representative is going to be a choice of one for each, such that they all glue together in a good way. Then, so points. So a point, we want to think of it as like not as necessarily like a localized point, but as a point of decision, either a yes or no that's consistent globally, right? So an ultra filter, right, is exactly this from our perspective, because we're thinking of our spaces as like topological spaces. So in itself, they are kind of spaces without point. They're like pointless topological spaces.
Mm-hmm.
That's this whole Heyting algebra thing. So the point of that is that we're not given points from the beginning, but we have to recover points after the fact. So we live in this topological world where everything is kind of fuzzy. And a point in that world ends up being a point of decision, especially because we're interpreting all the sets as sets of propositions, right? So from 7 sketches, we have this idea that a topos, which we remember is generally like, is a universe that acts like a sheet, the category of sheaves on a site. And site is the same, is important because Badiou uses the same term. But it lets us transform the question of just, is a proposition true or false in general to where is the proposition true, and treat that in a universal way, right? So then a point is going to be a point of decision, which gives a local set theoretical model about propositions being valid at that point. And then if they're valid at that point, they're going to be globally valid. So this is exactly what Reza was saying about the absoluteness. So here, from this perspective of points as a point of decision, they're absolute because when you can confirm that they're locally valid, you get a global validation as well. So Badiou describes the points as a, quote, local test of the transcendental of a world for the subject of a truth. So the points are going to be the place, it's going to be the location at which the subject in the process of trying to determine a truth is going to do like the experimentation, right? And there's going to be people, subjects that decide either yes or no on different propositions. And that's the important of the point, is like this very Kierkegaardian idea that where there's a choice, there's a place. So what this is meaning is that it's giving a, right, this is the same theme that we've been going on about like a spatialization of logic, right?
Mm-hmm.
And then so
I like that specialization of logic.
Yeah, so the body, right, in Badiou, this is like the stuff that's sort of left at the very end of Logics of Worlds, and he kind of, I think, rushes through some of it and doesn't maybe explore it like to the fullest extent. But the body is defined as the bearer of the subjective formalism, which makes truth and makes the subjective formalism appear in the world. So what that is going to mean that the body has parts that can sufficiently treat at least one point, aka the body, the parts of the body can make a decision within the world that was indiscernible before, and that could not, or that could not be decided before, right? So in relation to the Topos way of seeing this stuff, a body, we can interpret it as forcing new propositions into existence. Yeah. So this is just the last thing I wanted to cover, which is the conditions for a body to treat a point that Badiou gives at the very end of book 7, section 3 on the body. And he builds it up like in stages, right? So each one of these stages is going to be a subset of the previous, if you get it. And I like how he, for each one of these stages, he gave, like, rather than giving only a positive, or naming, rather than naming the positive situation, he names the negative in each stage. Okay, so that's all these italicized ones here. So the first one is going to be, a world must have points, which means that there are places in the world in which a decision can be made. And he says, otherwise the world is atonic, which means no points. So this is like the pointless topological space, where there isn't even a possibility, because of the structure of the parts itself, for any kind of choice, universal, absolute choice to appear, right? After this, there must be an event, which obviously comes being an event, spends a long time talking about that. But here, an event is going to be a maximally evaluated site. So it's a site which is something that brings the inexistent, right, something that had minimal existence, up all the way up until maximal existence. So it has to bring something that did not appear in the situation at all to suddenly appear. Okay. Otherwise, we're going to call the world stable. So a stable world is going to be a world where no change is even possible, because in existence never get past the point of even being able to register strong enough, right? And then after this, there must be enough elements of the site that are incorporated into the evental present. So the evental present, this is basically the elements that are mutually compatible with the event, and that treat the points of the inexistent. Here, and it's important that it has to be more than inexistent itself, because without the power, right, like the inexistent on its own will, without any support within the body of anything that comes above it, it won't have the power to like break through and appear in some sense like out of nothing, right? So he says in the other case, the worlds are here going to be called inconsequential, which means that if you don't have enough elements that physically support, this is like a materiality condition, that physically support the consequences of the event, then there's like, this is like there isn't even any, maybe something has happened, right? The event has occurred, there was some sort of possibility for a break, but there isn't anything pushing it forward such that it has momentum to keep going. The last two conditions are given for a specific point. So this is saying, okay, so we already have a point, we have something that we can decide on. So if there's something that we can decide on in the world, and there's enough support in that world in order to like, for the momentum to keep it going, there must be a non-empty part of it that decides that point. So it's a non-empty part of the body itself that must treat the point of the body. This is called the organ of it. And the final one is that the envelope of this part that treats it. This could be the organ. But the final one is that the envelope of the part that decides the point should be greater than the inexistent. So this is saying that for a specific point of decision, there needs to be an organ that has being in the world already that decides on that point. And then if this is not the case, then no point is treated, and then the world is inorganic. I'll admit that I'm a little, I don't know if Gabriel or Reza has.
I actually had a comment, but it's kind of orthogonal to what you're presenting, but it might be helpful to me, at least, because I'm trying to clarify for myself. I mean, I'm having a hard time really, I mean, you really help, but it's still hard sometimes to map. I think the harder thing, what makes it hard to map being an event logics of worlds is not logics of worlds, but the fact that the intricacies of Cohen's technique sometimes seems he explores them in so much detail compared to logics of worlds that it's hard to map each thing to the other. But then I had an idea, which I think it's too metaphorical, because it's not exactly the same thing. You couldn't say that the two things are technically related all the way, but it does seem like a useful intermediate step to at least clarify what parts of the technique are relating, which is Cantor's diagonal method. I just wonder what you guys think of this, because I mean, just in my head, suddenly some things clicked a bit better. So, for example, could you just put a blank page? I don't know if you have a slide with less stuff, just so I can write.
Yeah, I mean, right. 1 second. There you go.
Yeah, just so, for example, Reza, just see if this makes any sense to you guys. It seemed to me, right? Because so we're in the diagonal method, we want to produce a new number. We have the real line, then we select a segment of it, right? Which is kind of like our ground model, because we can work on this and the result was valid for this, right? Then we have something like a way of ordering this, which is we turn this into a list, a numbered list, so a countable list of real numbers, right? Here's one real number and so on and so forth. So this seems to be something like what Badiou is doing what Cohen's doing when he organizes these names. We know that when we list it like this, it is like a filtering of this segment, but we also have some added structure, because we know that when these numbers are ordered, we are, they have a relation between them, right? They are included in one another in a sense. Then he wants to show that, let's call this segment S, right? That I can produce a number S that is part of the segment, right? But it's not in this list, right? Then we have that kind of matrix kind of structure, right? Where we will just give like a number n, m for every digit, right? So this will be n2 for the same line, and this will be the first number for the second line, and so on and so forth, right? And then we're gonna filter this by going through taking the first, and this is gonna tell us that whatever our new number is, its first digit does not coincide with n1, m1, right? And then it's not gonna coincide with this, with n2, m2, and so on and so forth. So this would be like, we don't know what this number is, but we're constructing a way to describe it, right? So this would be, let's say, filtering through the conditions. so that these names are actually referring to something which is inside of the segment, but not named in the nameable in the segment, right? In our countable list. I'm just trying to understand if this sort of, it's a metaphor, because I think there's some step here that is trivial in the case of the diagonal argument, and that needs to be constructible. Like, it's not trivial in the generic technique, right?
It's technically it's not, it's conditioned, not constructed. Because if you construct it, then you know what it is, right?
Yeah, but we cannot construct this number either, because it has infinite many decimal places, right? But my point is that there's something trivial in the case of the diagonal argument. It seems to me there's some step that is not, I mean,
yeah, absolutely.
Coming, but you see, like, I'm just trying to understand if we can kind of, by analogy, associate some of these steps in the strategy to some of the steps that we've been discussing with the generic, because I think it might serve as a sort of more simplified common ground to make the connections with logics of roles, you know?
Let me share this. I mean, I'll send you this slides if it helps. But here, if I share this screen, this is precisely, we went through this previous one. This is the way that you condition G, which is exactly what you said. That you get bunch of dominations, you get each pi from each domination, and then you create a set out of these dominations. We define G is the filter that is dominated by at least one of the conditions in sequence A, which is this. This is diagonal argument. Like the entire set S is exhausted by these dominations, and then you take a condition from each of them.
Yeah. Okay. So our countable list of reals would be like the dominations.
Yeah.
Right. The Cantorian indexing here would give us, let's say, the material for the conditions. We're going to select out of these dominations, like we're doing here.
Yep.
And so once all of this is like just prepping that real segment so that we can then start constructing our number, right? So the construction of the number is like using this conditions, these pi conditions, right? To get some information about the number that we won't be able to construct anyway. Right? Because this is not, I'm not going to just use this. I'm going to link this to something that it is not. But so, for example, when I write the first digit of the number is going to be N1 M1 plus 1, for example. So it's going to differ in 1, the digit. If the original number was 1, this is going to be 2. So it's not going to coincide. It's not coinciding. So it's not just pi, right? It's pi indexing something else, right? Which is, from what I understand, the tuple. This is like a weird tuple, right? For this index, I have something else, right?
Mm-hmm.
So it seems like the analogy can be taken quite far. I wouldn't be able to, I mean, I found it's weird. I didn't find anything online about comparing forcing technique and diagonal numbers, though it seems like there is a history. Historically, people associate it, but not in terms of ideas, right? Of course, the diagonal method is much simpler. It's doing something smaller than that. It's proving something simpler as well. It's about, but it seems like you can actually, the analogy takes us far, you know, in clarifying what each of these steps are doing, if you refer them back to Cantor's method.
Yeah, forcing requires bigger sets of infinities too.
Guys, I have to leave.
Yeah, sure, but but this makes any sense to you guys? Like pursuing this sort of analogy. For example, I'm always trying to imagine how to present this thing, not only for myself, but also to people who have even less knowledge than me. And I feel like perhaps this could be useful.
I mean, the diagonal method, absolutely. I mean, absolutely is the way to basically show that G exists. Naming is a little bit different because naming, yes, builds something like a matrix like this, right? But there is no diagonality here, right? Because the purpose is different. Here in this space, you want to say that this is the absolute universe of all the names that we can build according to the schema. Now, what we want to do in order to name G is to prune some of this, which is the sheafification that that you said. So
yeah, I have to go back and look through this again. And I'll give you a better explanation next week.
so let me share this.
Sure.
If you want to send me your comments, that would be absolutely good, because then we can use this as a training or something later on.
Yeah, share this
No,
with us.
guys, but
I'd
you
like to look
clarified
through
a
it
lot
again.
of stuff. Yeah.
Sorry, my brain is fried.
Yeah, no. Let's end it here. But fuck, it was really helpful.
Okay, we can continue next week.
Now, continuous. Do you want me to present on forcing next week?
Let's see. I'm gonna add that discussion on the paper. If you guys probably, since that thing has
Let me
has
see.
kind of a time
1, 2,
frame.
3, 4, 5, 6, 7, 8, 9, 10, 11, 12 more slides on forcing.
Yeah.
This is a lot. There are a whole bunch of stuff that he proves, and then goes to the continuum hypothesis and stuff like that. Okay.
Yeah. Well, let's talk
Yeah,
through WhatsApp.
could you
then.
send this? I'd like to read through this again.
Sure. Sounds good.
Great.
Okay.
See you guys.
Okay. Take care.
Thanks, guys.
Thank you.
Bye-bye.